Okay, welcome. We are working on section 7.1, the area between two curves, and this will be example 5 and 6 on this video. And we encounter example 5 here, and it presents a new problem for us. I have the same curve laid out here and showing vertical versus horizontal rectangles. If I were to capture the area of this by using a vertical placement of rectangles, you may not notice any problem until I point it out. There becomes a place where the top function no longer continues to be the top function, and it's once I cross across that red dotted line. What you'll notice is that quadratic equation now is both top and bottom boundary for this region here. And for that purpose, when the top and the bottom switch, I can no longer just continue to use one integral. So if this were my top function, let's make it even more obvious. And here is the quadratic function. As my blue sweeps along, blue line, the linear function stays top until I get across the red dotted line. Now you can see how the pink curve, the quadratic curve, is both a top and a bottom boundary for me. So to calculate out the height of my curve, I've got to do it differently when I'm on the right side of the dashed line versus when I'm over on the left side. When I'm over on the left side, then I've got a different top and bottom. So that might present some problems. I would have to use two integrals. Not the worst case, but there is an easier way. And that easier way is to come at it using horizontal rectangles. So if I, let's make the same ones. Let's copy the linear function in blue and the quadratic in pink. You will see how the blue is always on the left and the pink curve always stays on the right. Its x values are larger at any position along here. So if I just took a bunch of horizontal rectangles, you can see, unfortunately they all have to be the same size when I do this, but you get the idea that, you know what, I could fill up this region by looking at horizontal rectangles, and then we just bring that differential, the change. Now the change ends up being change of y, doesn't it? The width of a rectangle is a change of y, or a dy, when we take it infinitesimally small. So this will be a little bit easier. I'll get by with one integral rather than two. This one I would have had to calculate it out as an area 1 and an area 2. Here I can get by looking at it as all area 1. So going back over to our notes here, this WRT stands with respect to x. So if I were to work this problem with respect to x, I would need two integrals. If I work this with respect to y, I'll need only one integral on this region from -2 to 1. Now, what will that look like? Okay, I can start my calculations here. The area is equal to the integral from some x value. Now, oh, is it an x value? Well, that's a darn good question, isn't it? It actually is going to be a y value, and you're going to see why. We're going to have some y value sub 1 and y value sub 2, because my equation on the left is already formatted. This was quite kind of the presenter here to present us a problem where these equations have already been solved for y, and I just wrote that in the wrong spot. Let's move that over here. That's our equation on the right, and then here is our linear function, x equals y plus 1. So I'm going to have my equation on the right, 3 minus y squared, take away the equation on the left, y plus 1. And then we already talked how the width of our rectangle is dy. Now what does this represent here? This actually is representing the horizontal length of our rectangle, isn't it? You can see it by the picture. If you think about when I put in some y value, maybe we're down here at y equals -2. When I put in y equals -2, I get out x equals -1, right? So we know I'd have to even be further down here so that I get a -1 as my x value. So when I put in -2 for y, I got out -1. And then over here on the right-hand side, when I put in y being -1 into this equation, x turns out to be 3 minus -1 squared, which is 3 minus 1 gives us 2. So I get the ordered pair on this side as we put in -1, we get out 2, -1. So if I want to calculate the length of my rectangle, it's going to be x equals 2 minus -1. It actually has a length of 3, doesn't it? And so to do that, I took my right function and subtracted my left function. And because they're written in terms of y, they are x values that I get. So I'm getting an x sub 2 minus an x sub 1 type value. And that will give us the length of the rectangle multiplied here by the width of the rectangle. It is very nice to see, why things work out the way they do. So I'm going to erase some of this and continue forward here. So we've got all this down. Now, I need to know where they intersect. I need to know this location as well as this location. Because as I integrate, it's integrating between these y values. This would be y2 and this let's call y1. So the distance between here is what we're going to be integrating from. y1, y2. To capture the intersections, let's take the equations and set them equal. So we're going to have 3 minus y squared is equal to y plus 1. I'm going to move everything to the right side on this, so I get a positive y squared plus y. Subtracting 3 will give us -2. This is factorable, hip hip hooray, and we get y plus 2 and a y minus 1. The points of intersection are going to be at y equals -2 as well as y equals 1. And that becomes my limits of integration. So -2, positive 1. So everything's just done in terms of y on this one. So now my area will equal -2 to 1 of 3 minus y squared. I'm going to take my negative and pass it through, -y minus 1 dy. We can update this, -2 to 1, -y squared minus y. -1 plus 3 gives us positive 2. And now you're ready to integrate. Integration is going to be the same. It's just add the power, divide by the new power, add a power up, divide by that power, bring on a y, evaluating it from -2 to 1. And then that'll be the same. Just use your fundamental theorem of calculus, and we should be able to get our answer. I turned out with an answer of 27/6, which is 9/2. Okay, let's look at example 6, and we have a graph given to us, and we have the function defined for us. So, reading here, the graph of the function g consists of a quarter circle, 3 line segments as shown below. Let f be the function defined by f of x equals the integral from -1 up to x of g of t dt. Now, we have encountered these before, haven't we? It's important to realize what the graph is. The graph is the g function. So I'm going to go over here and just note to myself this is g of x. Okay? And then I noticed that f of x is equal to the integral of g of t. So if I were to take the derivative of f of x, it would turn out to be the derivative of the antiderivative. And we know how to play that out. Put in x, and this becomes g of x times the derivative of x, which is 1. So I know my relationship. The derivative of f of x is equivalent to looking at the graph of g of x. So that's important to note. If I wanted to get to a second derivative of f, maybe I want to find inflection points or concavity, well then that would be a first derivative or the slopes of the graph that I'm looking at. So I like it if you would take the time to think about that and map it out, the relationship of these items. I think that will help make it easier. Okay, the very first question just asks us to find f of -5. So I'm going to have f of x. Well, let's go f of -5 actually. F of -5 is equal to, here's my rule, isn't it? So I need to take this stuff off. And it's going to say we're traveling from -1 to -5, because that was where x was, of g of x dx. G of t dt, I guess. Now, I notice, and I bet you did too, that I have a smaller value on top. So really, when I get my answer, I'm going to have the opposite of my answer, because I really do need to flip my integral over. All right, now what I need to do is the integral of this is going to be the area under the curve, isn't it? So this is the area between the curve and the x-axis. So from -5 to -1, we have a quarter circle. Let me put on the crayon here. We have a quarter circle in this first, taking us from -5 to -3. Then I run with a triangular region. And then to get to -1, I've got another triangular region. You know what? Let's put that in a different color. Let's highlight that one in maybe red. Okay. And that's the value of f of -5. So all we have to do is do a little calculation geometrically, and we've got it covered. I know that this is positive region, I know this is positive region, and I know that this is negative region. And I can clearly see that these two balance each other off and count as 0. So a quarter circle, here's the center of our circle, right? What is the radius? Well, the radius of our circle is going to be 2 units. So the area of a circle is pi r squared, and r is a radius of 2, so the total area of a circle would be 4 pi, but we only have a quarter of that circle, and so a quarter of 4 pi turns out to be just pi. Pi would be my answer to that question. Part B. It says, find all the values of x on the open interval between -5 and 4 where f is decreasing. Justify your answer. And for that, f is decreasing. Think back to chapter 3, the section where we learned about graphing mins, maxes, and so forth. We know that f is decreasing when f prime of x is less than 0. That will be when f is decreasing. So I need to look at its slopes, right? And f prime of x, we've already established that f prime of x is equal to g of x. So now I need to know, really, I need to look, when is g of x less than 0? So looking up at my board up here, where do I find g of x, which is the line graph I'm looking at, when is it below the x-axis? I would say that this is below and this is below the x-axis. So we are running from -2 to 1. F of x is decreasing. F prime of x is decreasing. You know what? I don't want to prime there. F of x is decreasing on the interval from -2 to 1 because f prime of x, which is equal to g of x, is less than 0 on this same region. Or you could repeat from -2 to 1. Clear? Part C. Part C, write an equation for the line tangent to the graph of f at x equals -1. So x equals -1. Now, recalling that f of x is defined using an integral, it makes it a little bit more difficult, but we're going to try and make this come back to something that's pretty easy. Just using basic knowledge of what we want to do. If I want to write the equation of a tangent line, I need two things. For a tangent line, I need to have a point and I need to have a slope. I know the x value for my point. It's when x equals -1. In order to get f of -1, then I'm going to put it into this function. And that's going to give me an integral traveling from -1 to -1 of g of t dt. And we all know that if I travel from -1 to 1, that ends up being a 0. That evaluates to 0. It covers no area. So I've got my point. I know that when I put in -1 into my function, I get out 0. So my point is going to be -1 comma 0. Okay, so that's part of what we need for a tangent line. The other thing we need is the slope. And the slope is, usually I take the derivative, don't I? I want to get the instantaneous slope at -1. So now I need to think about the relationship. How do I get the derivative of this? Well, that's the derivative of the integral. And they cancel each other off, or I go into the second fundamental theorem. Well, we had already established before we even did part A that f prime of x is equal to g of x. So f prime of -1 then would be equal to g of -1. And then I can just go to my graph, find g of 1, or g of -1. There's -1. Right here is my spot, isn't it? I'm going to have that location. So when I have -1, I come out with -2. The slope is -2. And then I can write my equation of my tangent line. Y minus y1 equals the slope -2, x minus -1. Clean it up, and we've got y equals -2, x plus 1. Okay, part D, find the minimum value on the closed interval -5 to 4. So really this encompasses that entire region, right? So we've got to consider all of that. I'm going to leave that line there. So find the minimum value of f. Minimum, when the word minimum is written like that, we interpret it as the absolute minimum. Absolute minimums, possible candidates for an absolute minimum is, well, there are going to be a few. The endpoints, if we are on a closed interval. And we are on a closed interval, so I'm going to have to consider when x is -5. I will also have to consider when x is +4. The other candidate for absolute min will be coming from any critical points. And remember, critical points are when the derivative of our function is equal to 0. Well, in this case, our derivative is equal to g of x. Now, if I'm looking for a min, I want to have F prime changes from being what? Going down to going up, so it changes from a negative to a positive. When I go to my graph, I'm going to be looking at g of x, and I want to look for when g switches from being negative to positive. And the place that I see that happening, here it is negative g, and then it switches to a positive g right there. So we indeed end up with a point right here at 1 that could be our critical point. So x equals 1 is another one that we want to consider because we know the derivative changes from negative to positive, and that's good. Okay, now how do we get our values? Well, I need to look at what f of these values are. So f of x. When I have negative 5, f of negative 5 is equal to, well, that will be the integral from negative 1 to negative 5. And we calculated that in part A, didn't we? G of t dt. And that turned out to be pi, so we have that answer already. And f of 1, let's go down and do that one next. F of 1 is equal to the integral from negative 1 to 1, g of t dt. And I need to go to my picture here. Let's clean this up a little bit. From negative 1 to 1, we're looking at this triangular space, and it has 1/2, the length is 2, the height is 2, and it is below the x-axis, so it is a negative region, so that would come out as negative 2. So f of 1 is equal to negative 2. Finally, the last one I need to look at is f of 4. And f of 4, we pick up some more, another triangular piece. So not only do I have the region from negative 1 to 1, and then I go from 1 to 4. So let's just write this out. This will be from negative 1 to 4, the integral of g of t dt. And I'm going to break it down. I know that this has a region of negative 2, and this region here will be 1/2 of the base is 3, the height is 1, so that will be 1.5, 1.5. With the negative 2, so I'd have negative 2 plus 1.5 gives me negative 0.5. And I evaluate each of these values looking for the least. I got pi, I have negative 0.5, and I had negative 0.2. Looks like the winner is, oh darn guys, I just looked at my notes. Was that a negative pi? It was, because remember we had to flip this flipped around, didn't it? So this here had to flip around, and that gave us the negative pi. So the winner, let's declare a winner here, is f of negative 5. So starting on the left endpoint would be the absolute min for the function. All right, that's quite enough for this one, and the only one I have left is problem 7. Thank you.